Welcome to the deep dive. You know that feeling when you're sitting in a presentation, maybe a lecture or some crucial meeting,
Oh, yeah.
and the speaker clips to the next slide and suddenly, boom,
Mm.
you are just hit with this massive wall of dense, unreadable mathematical equations.
It's the worst.
There are subscripts, superscripts, Greek letters everywhere, and you can just feel your eyes immediately glaze over.
It is a totally universal, almost visceral reaction. You go from actively listening to the speaker's voice to suddenly playing this highly stressful game of symbol matching in your head.
Exactly.
Your brain is desperately trying to map all these abstract characters to the concepts they actually represent. And, the actual message of the presentation is just completely lost in the noise.
I've been in so many meetings where my brain just hits a brick wall at that exact moment.
Hmm.
And usually we kind of just accept this as a necessary evil of technical presentations, right? Like
Wow.
we assume math is just hard to look at.
Right, we just deal with it.
But today we are exploring a 2026 slide deck presentation by a developer named Luck036. It's titled Making Math Colorful, Adding KaTeX Colors to Slide Decks. And let me tell you, this completely changes the game for anyone who has to present complex information.
It really does. It tackles something we've broadly accepted as just a fundamental flaw in how we communicate complex ideas, and it offers a surprisingly elegant, visually striking solution. The premise is that the difficulty isn't necessarily the math itself, but the visual friction of our delivery mechanism.
Okay, let's unpack this. Our mission for this deep dive is to explore how applying what the author calls semantic color coding to mathematical equations can completely transform them from an intimidating wall of symbols into this instantly readable visual language.
Yeah, visual language is the perfect way to phrase it.
And perhaps even more wonderfully chaotic, we are going to uncover the surprisingly complex technical journey of actually implementing this across dozens of files using artificial intelligence.
Because having a great design idea is only half the battle. Actually executing it across thousands of lines of code, specifically mathematical formatting code, is a completely different beast, as the author very quickly discovered.
Oh, for sure. But before we get into the wild world of AI automation, we really have to talk about the core problem. The deck refers to this as the wall of math problem.
Right.
Let's say you are sitting in a typical 30-minute talk. The speaker is talking, but you are staring at a variable on the screen, something like x_v. You're sitting there trying to remember, wait, is v a set? Is x a parameter?
Did they define that on the last slide?
Exactly. You completely lose track.
Well, every single second you spend context switching, trying to decode the structural meaning of the symbols on the screen, is a second of lost learning. Your cognitive load just maxes out trying to parse the sentence structure of the equation.
Yeah.
That leaves you with basically zero biological brain power to actually absorb the concept being taught.
I was thinking about it like this, actually. Trying to read uncolored flat equations is kind of like trying to read this massive, complex Russian novel where every single character is just named John.
That is a brilliant analogy.
Right. You spend your entire time trying to figure out which John is talking to which John, and you completely miss the actual plot of the story.
Exactly. When every symbol looks exactly the same, they lack structural identity. To fix this, the author turned to a specific pedagogical foundation. What's fascinating here is that this isn't just about making the slides look aesthetically pleasing.
Right. It's not just decoration.
No, it's grounded in two major psychological concepts: dual coding theory and pre-attentive processing.
Okay, I've heard of dual coding theory in the context of learning. It's the idea that if you combine text and visual cues like color, they reinforce each other in the human brain. You aren't just memorizing a letter, you are linking a mathematical concept to a visual marker, which creates a much stronger memory pathway. But the second one, pre-attentive processing, that implies something happening before we are even consciously paying attention.
Pre-attentive processing is the real magic here. Biologically speaking, when you look at a black and white equation, your eyes send that data to the language processing centers of your brain, like Wernicke's area.
Okay.
Parsing those letters takes time and active cognitive effort, but color is processed by the visual cortex at the back of your brain in milliseconds before conscious thought even kicks in. It completely bypasses the language bottleneck.
Oh, wow. So if a speaker uses a consistent color scheme, the audience's visual cortex actually recognizes the structural roles of the math before their conscious brain even begins to, read the individual letters and numbers.
Yes, they see the relationships instantly.
That's wild. The audience is passively absorbing the structure without having to burn any mental calories.
Exactly. The color is doing the heavy lifting for your short-term memory. You don't have to consciously remember that V is a set because your brain has already registered the color assigned to sets.
But wait, I have to challenge this a bit.
Sure.
If we just start tossing colors onto every single variable on a slide, isn't there a massive risk of turning these presentations into a confusing rainbow explosion?
Oh, absolutely.
Like if a slide has 50 variables, isn't the audience still going to be completely overwhelmed by the sheer amount of neon on the screen?
That is the exact trap that most people fall into when they first try to format slides. They treat color as a decoration, highlighting things just to make them pop. The author is very clear that this approach will ruin the effect.
So how do you avoid that?
To prevent the rainbow explosion, colors must denote strict, unchanging structural roles. It is all about semantic meaning and absolute consistency.
I see.
The author actually outlines 3 highly specific color schemes used for different mathematical domains, evolving from basic optimization to complex geometry, just to prove how this works in practice.
Okay, yeah. The first scheme they detail is called the primal dual scheme, used in algorithm and optimization decks.
Right. In this canonical palette, every color has a dedicated job. Salmon, which is a sort of pinkish orange, is strictly used for sets.
Okay.
So if you are looking at a vertex cover problem, which is all about finding the smallest set of vertices to cover all edges in a graph, every time a set is mentioned, it is salmon. Lime green is for edge sets or paths. Coral is reserved for weights and parameters.
And then the actual variables themselves are split between primal and dual, right? Like the primary decision you were trying to make versus the constraints you were working under.
Exactly. Regular green is for primal variables, and fire brick, which is this deep, intense red, is for dual variables.
Oh, fire brick. That sounds intense.
It is. When you look at an equation for that vertex cover problem, you don't just see a jumble of letters. You instantly see the green primal variables interacting with the coral parameters, all organized within the salmon sets.
And I imagine when you flip to the next slide to look at the dual linear programming version of that problem, the equations are suddenly filled with that intense fire brick red. It just screams, hey, we're in a different mathematical space now, without the speaker having to utter a single word.
It acts as an instant visual anchor. But what happens when the math moves away from discrete optimization and involves continuous fields or opposing forces?
Right.
That brings us to the second scheme, network optimization. This one focuses heavily on the concepts of flow versus tension. In this palette, green represents flow or co-boundary elements, while blue represents tension or boundary elements.
The deck shows this incredible example using Stokes' theorem. For anyone who hasn't taken advanced calculus, Stokes' theorem calculates the curl of a vector field across a surface. And I mean, written out normally, it looks like absolute Greek alphabet soup.
It really does. It's terrifying.
But the author color codes it so that the flow elements are green and the tension elements are blue. It turns this terrifying calculus concept into a visual balance of forces. You can literally see the flow moving across the equation.
If we connect this to the bigger picture, this isn't just about slide formatting anymore. It's about using color to reveal the hidden mechanics of the universe that math tries to describe. Take the third scheme they mention, projective geometry.
Oh yeah. In projective geometry, you are often dealing with point-line duality, right? The idea that points and lines are basically interchangeable in certain theorems.
Precise.
That dual color scheme in the deck assigns salmon strictly to points and their coordinates, and steel blue strictly to lines. They are essentially color-coded rivals on the screen.
Pitting those two opposing roles against each other visually clarifies everything. If you are looking at a formula for a cross ratio, you never have to ask, wait, was P the point and L the line?
Right, because the salmon tells you it's a point.
Exactly. The colors answer the question before your conscious brain even formulates it. And because that same symbol has the exact same color, every single time across every single slide, it acts just like syntax highlighting does for software engineers. It builds a persistent visual language.
Which is intellectually just so satisfying.
Yeah.
But here is where we hit a massive roadblock.
Mm-hmm.
Designing these beautiful, meaningful color palettes is one thing. Actually applying them, well, that is where this story takes a wild turn.
It sure does.
Because if you were trying to code this yourself, you were looking at applying these highly specific KaTeX color tags to over 100 equations per file across roughly 75 different Markdown and HTML files.
Doing that by hand would be an administrative nightmare. It would take weeks of tedious, mind-numbing data entry. You would be manually typing \color bracket, salmon bracket thousands of times.
Nobody wants to do that.
And humans are notoriously bad at repetitive data entry. You would almost certainly introduce syntax errors that would break the math rendering entirely.
Here's where it gets really interesting. The author didn't do it by hand. They decided to bulk colorize everything using what they called parallel visual engineering subagents.
Yep.
They basically unleashed artificial intelligence on their slide decks.
It was a highly ambitious delegation strategy. The workflow was designed so that each task consisted of one file and one specific color scheme. An AI agent would be assigned to read the file, understand the mathematical context, apply the exact color to symbol mapping, and then output the formatted file.
I mean, it sounds perfect in theory. Give the AI the rules and let it run. But reading through the implementation section, the reality of working with large language models on raw formatting tasks is hilarious.
It's a mess.
It's like hiring an eager intern to clean your desk, and they write you a brilliant 5-page essay on why a clean desk is important for workplace productivity, but they don't actually pick up a single piece of trash.
The essay analogy perfectly captures the behavioral tendencies of modern AI. The author ran into two massive hurdles while trying to automate this, and it reveals a lot about how these systems actually function under the hood. The first was queue saturation.
Right, so the author initially tried to launch these AI tasks in massive parallel batches to save time. Launch 50 agents at 50 files all at once. But they quickly learned that if you launch more than 20 concurrent tasks, the background task queue just completely saturates and everything fails. The system buckled under its own weight.
This happens because of API rate limits and the massive memory overhead required to maintain the context window for 20 independent large language models simultaneously.
Makes sense.
Each agent needs to hold the entire markdown file, the complex system prompt, and the color mapping rules in its active memory. When the background task manager gets overwhelmed by those concurrent memory states, it just starts dropping connections.
They had to slow it down.
Yeah. The lesson learned, and strictly noted in the deck, was that they had to throttle the automation. They were forced to relaunch the tasks in much smaller batches of 10 or fewer. Send a batch, verify it, send the next batch.
But even when the batch size was fixed, they ran into challenge 2, which is the absolute funniest part of this entire deep dive. The author refers to them as agent no-omps, the phantom completions.
Oh, you have to picture the author sitting at their computer watching the terminal as the AI agents work. An agent flags that it has successfully completed formatting a complex math file, but the completion time is listed as 0 seconds.
0 seconds. The AI would do this incredibly elaborate, intelligent-sounding analysis of the file. It would identify the vertex cover variables, explain exactly what needed to be colored based on the prompt, and then just stop.
Yep.
It wouldn't output any edited code. It would just say, task complete.
This exposes a fundamental issue with how these models are trained. Through reinforcement learning from human feedback or RLHF, these models are heavily incentivized to be helpful, chatty conversationalists. They get rewarded during training for summarizing plans and giving thoughtful analysis. They do not naturally want to do raw, silent, repetitive text replacement. Doing the actual formatting work goes against their conversational training.
So the cutting-edge AI just wants to chat about the math rather than actually formatting it. To fix it, the author literally had to start shouting at the agents in the system prompt. They had to resume the sessions with the all-caps command, apply the edits now, and explicitly instruct them not to stop at analysis.
It requires aggressively overriding the AI's default behavior. But this brings up a crucial engineering problem. How did the author actually know if the agents were doing it right?
Yeah, good point.
If you can't trust the AI when it says it's done, how do you verify 75 heavily modified files without reading every single equation yourself?
This is where the author's engineering background really shines. They didn't rely on the AI's self-reporting. They used a completely objective, old-school developer utility, grep count.
Nice and simple.
Grep is basically a command line tool for searching plain text data. They simply counted the number of times the exact string \color bracket appeared in the file before and after the agent touched it.
It is a beautifully simple verification method. If a file called lec060remark.html went from having 63 instances of the color tag to 166 colored equations, the author had objective mathematical proof that the agent had actually done the heavy lifting.
Yeah.
They had a whole automated checklist. Did the tag count increase substantially? Were the $ delimiters for the math blocks perfectly balanced? Did the AI accidentally touch the standard code blocks or mermaid diagrams?
And what happened if an AI agent just completely refused to cooperate? Because we all know those files exist, the stubborn edge case files that just constantly confuse the model.
For the most stubborn repeat offender files, the author had to abandon the AI entirely.
Really?
Yeah, they created a fallback plan using a deterministic Python script. A Python script doesn't hallucinate, it doesn't want to chat about its feelings, and it doesn't do no-ops.
It just does the work.
Exactly. It just uses regular expressions to find the exact symbol and replace it with the color tag. For one specific file, lex07.md, the Python script flawlessly executed 90 replacements, bumping the colored lines from 97 to 149.
So sometimes you just have to roll up your sleeves, write the deterministic code, and do it the old-fashioned way. But despite the AI drama, the sheer scale of what they accomplished is wild. In the end, in a single massive push, the author committed 75 files with exactly 2,562 insertions of color formatting.
2,562 precise semantic changes. And out of that massive undertaking, the author developed a very strict set of rules, the do's and don'ts of math coloring, for anyone who wants to replicate this in their own presentations.
These rules are vital because if you break them, you ruin the pre-attentive processing we talked about earlier. The primary do is obvious. You must color structural roles like sets, edges, and variables, and you must maintain consistency across your slides. But the don'ts are almost more important. The author explicitly warns, you must not color the clutter.
Right. Leave plain numbers alone, leave text like min or max or log neutral. Do not color the big O notation for algorithm complexity, and definitely leave algorithm step sizes like alpha or beta entirely neutral.
Because if everything is highlighted, nothing is highlighted.
Exactly.
It is the concept of signal-to-noise ratio in design. If you color a plain number 3, what semantic role does that play? None. It just adds visual noise to the slide. The goal is to make the mathematical structure pop. If the noise remains neutral, black or white, the colorful structure stands out even more. You're physically guiding the audience's eye to what actually matters.
But of course, because this is a technical implementation, there is one massive, highly specific gotcha that the author warns about regarding how these slide decks actually render in a web browser.
Oh boy.
It involves the document object model, or DOM, and a race condition between two JavaScript libraries. KaTeX, which renders the math, and Remark.js, which creates the slide markdown. The order in which these scripts run is life or death for the presentation.
I think I can deduce why this happens. I understand that markdown parsers like Remark use underscores to create italics and curly brackets for specific formatting. But in mathematical equations, KaTeX uses underscores for subscripts and curly brackets to group items together. If they run at the same time or in the wrong order, doesn't the system get totally confused?
You hit the nail on the head. If the Remark markdown parser runs before the KaTeX math renderer, Remark will look at your beautiful complex equation, see an underscore meant for subscript, and say, they want this italicized. It will completely mangle the underscores and brackets inside the math blocks, destroying the equations before KaTeX even has a chance to turn them into math.
So the absolute rule is KaTeX must run first. You have to pre-render the math, hide it from the markdown parser, and then let Remark process the rest of the text on the slide.
A function called renderMathAnElement has to fire, then Remark can create the deck, and finally you can initialize any diagrams. It is a strict 1, 2, 3 sequence. If you mess up that sequence, your 2,500 beautiful color insertions turn into broken text.
So what does this all mean? We spent this time talking about slide deck formatting, AI agents refusing to do their jobs, and the render order of JavaScript libraries. But looking at the bigger picture, this entire project isn't really about code at all. It is a masterclass in empathy.
Empathy for the audience. The author realized that their listeners were struggling, not because the underlying mathematics were too hard to grasp, but because the delivery mechanism itself was fundamentally flawed.
By utilizing the neuroscience of color and pre-attentive processing, they didn't dumb down the data, they just removed the friction of understanding it. They stopped asking their audience to actively decode complex symbols and allowed their visual cortex to just effortlessly recognize the patterns.
It's taking the heavy burden of translation off the audience and placing it squarely on the design and the presenter. From understanding the biology of how our brains process color, to designing those strict semantic palettes for primal dual optimization and projective geometry.
right through the chaotic, pull-your-hair-out realities of wrangling stubborn large language models to forcefully edit 75 files and verify thousands of lines of code. It's a complete journey from a brilliant psychological theory to a very messy, very real-world technical practice.
And looking at what Lux036 achieved here, this raises an important question. If semantic color coding can so entirely revolutionize how we decode complex, intimidating mathematics, what other dense, text-heavy areas of our modern lives could benefit from this exact same approach?
Oh, that's a great point. Think about impenetrable legal contracts or incredibly confusing medical bills. What about those labyrinthine software terms of service that we all just blindly scroll past and agree to because the wall of text is too exhausting to read?
If we applied a universal semantic color palette to their structural roles, coloring the obligations one way, the financial penalties another, the covered services a third, we could bypass the language bottleneck entirely. Could we instantly clarify massive bureaucratic systems that are currently designed to overwhelm us?
Imagine looking at a 4-page medical bill and your visual cortex instantly registering exactly what insurance covered in green and what you owe in coral without you having to consciously decipher a single grid or code. It's the exact same wall of math problem, just in a different font. The potential applications for pre-attentive processing are everywhere once you know what to look for.
We just need the engineering patience to actually implement it.
And maybe a few Python fallback scripts, just in case the AI decides it would rather write an essay about the medical bill instead of formatting it. Well, on that note, we want to thank you for joining us on this deep dive. The next time you find yourself staring at a wall of dense, overwhelming information, whether it's a presentation slide full of equations or a legal contract full of jargon, take a moment to look at the clutter in your own life. You might just find that applying a little semantic color could bring the whole picture into focus. Until next time.